Okay, welcome back. So as promised, we're going to take this up a notch and start looking at some more interesting polyatomic ions. And one thing that I thought would be good to start with is the nitrate ion. So we've got NO3 minus as our formula. Um, I'm going to go through the list of steps, but I'm not going to write them out again. Step number 1 then was to tally up the number of valence electrons. So here we go. Nitrogen has 5. Let me tally it up here actually. We've got 1 nitrogen plus we have 3 oxygens. And there is a negative charge on this ion, so we have to add that in as well. And that means that we're going to add 1 extra electron because of the negative charge. Okay, so our nitrogen has 5 valence electrons. We have 3 oxygens, and each oxygen has 6 valence electrons, and then we add 1 for the negative charge on the nitrate ion. That's going to give us a total of 24 electrons. So now we know what we want to do. And sometimes the way I like to think about this is that we gather all the valence electrons and we throw them into a bowl. We place our atoms on a diagram, and then we dish out the electrons back again. So again, it doesn't matter where the electron originated from, which atom it came from. We're just putting all the valence electrons together, and then we are redistributing them. So step 2 then has us give a central atom. We want to place our atom symmetrically about our central atom. Nitrogen is the loner, so it's going to be the one in the middle. And if I put my oxygen atoms around the nitrogen, I have now accomplished step 2. Step 3 says to place a bonding pair of electrons between the central atom and each one of the surrounding atoms. So far so good. Step 4 says complete the octets of my surrounding atoms. Okay. All right, now that's done. Okay. Step 5 then, what I need to do is decide whether or not I have any electrons left over. And if I do, part A of step 5 tells me that I have to put them on my central atom. So if I count up these electrons, what I'm going to see is that I in fact have 24 electrons on my diagram. Well, I started with 24 electrons. So step 5A is not relevant. I don't have any extras to put on my central atom. 5B, however, has me investigate whether or not my nitrogen atom has a complete octet. In this case, nitrogen does not have a complete octet. My advice from my list of steps says that if the central atom has an incomplete octet, then I use double bonds to the surrounding atoms. So what that's going to look like is I'm just going to redraw what I have. And I can pick one of my oxygens and I can say I will move a pair of electrons from this position. I will shift it in between the nitrogen and the oxygen, and in so doing I will form a double bond. Okay, I hope that that's clear enough for you to see. And so what this diagram is going to look like, if I move it from left to the right side of my page, I'm going to end up with 2 oxygens that were the same as they were, but this last oxygen has its pair of electrons has shifted into position between the nitrogen and the oxygen. And now that's what I've got. So it looks like I formed one double bond from an oxygen to the nitrogen by moving a pair of electrons in between. All right. Now the last piece of this is, sorry, now nitrogen appears to have a full octet. Everybody's happy. Okay, everyone's got a full octet. This, however, is a charged particle, and what you might remember from doing Lewis diagrams of ions is that in order to indicate the charge on this particle, I have to draw square brackets around it, and I have to indicate the charge on the outside. So this is the correct Lewis diagram for a nitrate ion. There is a little bit more to it than this, okay? And what you did was you watched me borrow electrons from this oxygen and put them in between nitrogen and oxygen in order to form a double bond. I chose this oxygen, but either one of these oxygens would do. They are all equally likely to do the same thing. So in order to show that it could have been any one of these oxygens that contributed the pair of electrons, what I have to do is I have to draw the nitrate ion, and instead of just drawing all kinds of dots now, what I'm going to do is I'm going to represent the bonds with straight lines. So the one that I have done looks like this. Okay, a single bond is a pair of electrons. A double bond is two pairs of electrons. I'm going to draw my unpaired electrons, okay, and that is one possible structure of a nitrate ion. The other possible structures I represent with this set of push me pull you arrows. This is one possibility. And there's one more possibility where the double bond is up here. And we're going to talk more about all of these things. This is just a little bit of a view to get us started. But all three of these possibilities are equally likely. In fact, they interchange between each other so quickly. The electrons in this double bond spend part of their time here, part of their time here, and part of their time here. They move around these three structures so fast as to make each one of these NO bonds identical. Identical in length, identical in strength, and what we say is that the bond order is 1 1/3. Now think about what that means. So the NO bond order is 1 1/3. Each one of these is at least one bond. But the second bond spends 1/3 of its time here, 1/3 of its time here, and 1/3 of its time here. So it's stronger than a single bond, but not as strong as a double bond. And each one of these bonds is identical. Okay? So this is the structure then of a nitrate ion. You can imagine, and when we get to the next videos, what the shape is going to look like. It's going to be relevant to what we come up with in terms of its structure. Okay? Building a Lewis diagram is the first part of that. Now just to finish off, I'm going to do one more ion, and we're going to do the nitrite ion. A lot of things are going to be similar. And this way we will be able to tackle the last piece. We'll be able to tackle item 5A, okay, of our list of steps. Okay, so here we'll look at the nitrite ion. That's NO3 minus. First step is to tally up the valence electrons. Well, we have 5 from nitrogen. We have 2 oxygens, each with 6 valence electrons, and we add 1 electron because of the negative charge. That's going to give us a total of 18 electrons. Those are what we have to work with. So we'll get started. Step 1, I'm going to draw my atom arrangement. I'm going to put a bonding pair in between my central atom and my surrounding atoms. I will complete the octet of my surrounding atoms. And what I can see is that by the time I get to this stage, and this is step 4 now, what I need to do is, step 4 was completing the octets of everything. Step 5 says that if I have any electrons left over, I have to dump them on the central atom. Well, this is a case where I do have some left over. I've put 16 electrons on my molecule, and I started with 18. So I have 2 that haven't been put on here yet. Those 2 will end up on the central atom. I'm going to put them on right now. Okay, you can see from following along my diagram the order that I'm doing things in. The reason why I would have drawn this out stepwise and drawn each evolving stage is so that you can see the differences from the beginning to the end in a gradual way. Okay, I'm hoping that we're beyond that now. Okay, so I have all 18 electrons on. This was your example of step 5b, where I put the extra electrons on the central atom. Sorry, 5a. 5b says if nitrogen has an incomplete octet, then I have to complete it by contributing pairs of electrons from the surrounding atoms in order to make double bonds. So I think you can see that that's going to be necessary here as well. I've only got 6 electrons around my nitrogen atom. So what that means then is I can take, and I'll draw this out like I did before, I can take a pair of electrons from one of the oxygens, shift them into position between the nitrogen and the oxygen, and in that way I can form a double bond between oxygen and nitrogen. Okay? If I were to draw this as a line structure, which is sometimes a little easier to see than these dots, that's what I'd have with a lone pair on the nitrogen. Okay? It's a charged particle, so I'm going to put square brackets around it, indicate the charge outside. But like with the nitrate example, I could just as easily have pulled electrons from this oxygen and made a double bond here instead of here. Because both of those possibilities are equally likely, I have to indicate that with my push me, pull you arrow, show the other possibility as the other resonance structure, and understand that these two possibilities interchange so quickly so as to make the nitrogen-oxygen bond lengths indistinguishable. Bond lengths, bond strengths are all identical. And that would mean that each one of these bonds would have an order of 1.5. Okay, and if you want to think about why that's true, I have at least a single bond in both cases, but the second bond is shared equally between two pairs of atoms. Okay, so I've got a half a bond extra here and a half a bond extra here, and that's where the 1.5 bond order comes from. Okay, so that's it. That's sort of like your new way of doing Lewis diagrams. You have a chance to practice some more of these from your textbook. And in order to work on the next set of videos, in order to work on the VSEPR sheets, you have to start with a proper Lewis diagram. We will talk about exceptions to the octet rule. Some of that's mentioned in the upcoming videos. The exceptions to the octet rule are possibly that we do not achieve a full octet on our central atom. And then the other things we've seen with PCl5 is that there are some times when our octet is exceeded. And we'll talk about whether or not to feel comfortable about either of those things. Okay, so the next part then is once we have a Lewis diagram, then we can start making decisions about the three-dimensional structure of our molecules and polyatomic ions. So stay tuned for all of that, and thanks for listening.